All right. So where we are is we can draw Lewis structures. We can calculate or figure out the bonding, number of bonds, number of non-bonding electron domains. We can figure out the shape of a molecule. And then the last thing we added last week was looking at electronegativity with the shapes to figure out if a molecule is polar or not. Okay. And it truly is that polar or not question. That's kind of the most important part of this whole thing. That's what the lab we're going to do later this week is going to be all focused on, where we start to look at some more chromatography type stuff. But the last little bit of this unit is really about the sort of theoretical underpinnings. Okay. We started last unit, we spent a lot of time developing atomic orbitals. We learned about electron configurations, s orbitals, p orbitals, d, f, all those kinds of things. Okay. But when we take and think about a molecule like methane, CH4, okay, this carbon has 4 bonds. If you go in the lab and you measure them, you know that the bond angle is 109.5, that these bonds are all identical. Like we can't tell them apart. Okay. It's a symmetric molecule. If you think about a carbon atom, however, and you say, hey, carbon, an s orbital, 3p orbitals in its outermost, right? That valence shell that we said does all the chemistry work. How do we get this shape? The p orbitals are at 90 degrees to each other. The s orbital is a sphere. This shape doesn't come naturally out of any of the, sorry, I'm recording. That's why I don't want you on camera. So, um, I just have a little bit of extra editing to do. No big deal. So this shape does not come naturally out of a spherical S or 90-degree angles for p orbitals and things like that. So here's the situation. We can take our atomic orbitals and come up with a semblance of an explanation. I want to point out that this is not necessarily a great way to think about these things. It works, you get roughly the right pictures and stuff, but a more modern take would be to say, hey, let's think about this as a single unit and do the wave function for the whole thing, what we would call molecular orbital theory. And then we'd be solving the wave function directly instead of taking the results of the wave function and doing some funky thinking about it. Okay. So everything I'm about to teach you is sort of a in between intermediate step of trying to bring more quantum mechanics into Lewis structures and localized electron models, which we already know is just not a great idea because they just don't mesh together. But it's a way to try and explain how do I get this shape when I start with an s orbital and 3p orbitals. Okay. And so the idea is we take those orbitals and basically throw them into a blender. Okay. I'm going to take 3p orbitals and 1s orbital, and I'm going to mix them together mathematically. Remember that when we talked about atomic orbitals, we said, oh, each of these lobes in the p, there's a positive, negative, positive, negative, positive, negative, and the s by convention is just positive. Well, if you combine those 3p orbitals with their positive and negative bits and s orbital, you can generate 4 new orbitals that are all equivalent, that are all the same. Okay. You get 4 bonds, 4 orbitals around the carbon that are all the same. We call these new orbitals hybrid orbitals because we've generated them by hybridizing or combining the S and the P. To keep track of them, because there are different kinds, depending on what orbitals you put in, we have a notation system, okay? And so there will be questions and they'll say, hey, look at the carbon in this molecule. What is its hybridization. And they want you to identify how many bonds or electron domains, I should say, have been combined together to create the new molecular hybrid orbitals. All right. So in this case, we took an s orbital and we combined it with three p orbitals. So we say the new orbitals are sp3 hybrid orbitals. A single s orbital combined with three p orbitals. The superscript notation here is just how many p orbitals did you combine. Mathematically, it looks something like this. If you take these s orbital and the three p orbitals, these things will cancel out. Part of the p orbital cancels out with the s orbital, and part of it adds together. So these four new orbitals are all exactly equivalent. They point at 109.5 degrees, and you can see they still double lobed shape, but there's a little tiny baby lobe and a bigger, larger primary lobe. Okay. And that is a way to visualize, think, how did I get a tetrahedral 109.5 degrees from atomic orbitals? All right. Now, obviously, not all shapes, not all molecules have four bonds sticking out at 109.5. We've seen plenty of other examples where there is trigonal planar, right? Linear. There are other shapes. So, if we think about generating those, you can actually do the same process by using fewer p orbitals. So, for instance, if I'm going to have a trigonal planar shape where I have three equivalent bonds, three bonds that are all the same, you can mathematically get that by taking an s orbital and combining it with two p orbitals. You mix them together and you get three orbitals, three bonds that are all in a flat plane. Mathematically, we're just leaving out the ZP orbital. In this case, once again, we get three new orbitals that are all exactly the same and are in a flat plane at 120 degrees. You still have that little baby lobe and the big one that does the bonding because of the addition subtraction phase stuff from the atomic orbitals. Okay. Now, finally, so remember we started with sp3. This one was sp2. The final one is just sp. Okay. So sp2 equivalent bonds, we're just going to add an s orbital with a single p orbital. And when we do that, we get two orbitals with that same sort of big lobe, tiny baby lobe. The bigger part of the lobe is the one that does the bonding. So hybridization is in a way to attempt to explain the shapes that we see molecules actually having and reconcile that with atomic orbitals without going through and resolving for the wave function and solving the wave function for the whole molecule, which would be a better bet. That would be a better way to do this. It's just more complicated and generally not something we do during first year chemistry. To summarize, what you're going to have to do, the problems you're going to see are going to require you to draw a Lewis structure and pick an atom and determine how many electron domains are around that atom. You need to be able to count to four. Okay? You count up the electron domains. If an atom has two electron domains, that means that it has this linear structure and it is sp hybridized. There are two electron domains. Okay. If there are three electron domains, it's sp2 hybridized. And it would have 3 electron domains. You'll notice in the images I'm showing here, there are these hybrid orbitals outlined in blue. Those are the ones that are actually exist. Those are the ones that have hybridized. Each time we take and add more p orbitals, there in the sp, there are 2 p orbitals that don't participate in hybridization. And you might ask yourself, how can that be? What do you mean they don't participate in hybridization? I say, patience, grasshopper, we'll get there in 2 slides. So sp2, 3 electron domains, okay? sp3, all the p orbitals and the s orbital, everybody involved, that has 4 electron domains. Now, before anybody raises their hand to try and get the chocolate coin, the notes go on to talk about D sp3 and D2 sp3. So I want to highlight this. Nobody thinks that d orbital hybridization is good chemistry anymore. Okay? So the ACS, American Chemical Society, the College Board, IUPAC, everybody has said, hey, we're not even going to teach this anymore. It's not a good model. It's not right. It's not how things behave. Okay, so if you'll notice on the notes, there are 2 more rows. You should cross those off. I left them on there so I could specifically say d orbital hybridization is no longer considered good chemistry. It's not what's taking place. It's a bad model, so we don't teach it. This is an okay model. This is kind of what's happening, but it is actually quite a bit more complex, and we should truly use something like molecular orbital theory to try and explain molecules. But that's for a later class. You need more calculus to be able to do that kind of stuff. Now, how does this work? What problems are you going to see? Okay, so 2 examples. Right now, in the example box, write down the Lewis structure for NH3. There's a little example box at the bottom of the page. Write down the Lewis structure for NH3. So you got an N, you got 3 H's, 5 electrons from the nitrogen, 3 from the hydrogen, and in the middle, 3 bonds, non-bonding pair at the top, right? We've done this one a whole bunch. That should be pretty straightforward. So you get something that looks like this, right? You've got 3 bonds, and 1 non-bonding pair. The electron geometry is what? Take a sec. Think about it. Don't say anything. What electron geometry does NH3 have? Check with your neighbor. So electron geometry means I don't care if it's a bond or a non-bonding. Electron geometry versus molecular geometry. The electron geometry takes everything into account. So 1, 2, 3, 4 electron domains is tetrahedral. Now, molecular geometry. Molecular geometry cares if it's a bond or a non-bonding pair. Molecular geometry, 3 bonding domains, 1 non-bonding domain means trigonal pyramidal. Trigonal planar would be 3 bonding, 0 non-bonding. 3 and 1 is trigonal pyramidal. Okay? So a triangular base pyramid that comes up to a point, trigonal pyramidal. For hybridization, we want to focus on the electron geometry. We just want to count. We don't care if it's a bond or a non-bonding. How many electron domains are there? Okay, so how many electron domains? You've already done it. 1, 2, 3, 4. Now you need to add 4 orbitals together for the nitrogen atom, right? Around the nitrogen, there are 4 electron domains. So you say, take an s orbital and add in 1, 2, 3 p's. Why 3? Because I had to get to 4 electron domains, 4 orbitals. So 1 s orbital, 3 p orbitals, mix them together, and you get 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. So if somebody said, what is the hybridization of the orbitals in the nitrogen in ammonia? You would count 1, 2, 3, 4 electron domains, sp3 hybridization. That's got 4 letters in it, an S and 3 Ps. Okay? Do the Lewis structure for methanol. Methanol, also known as formaldehyde, H2CO. Do the Lewis structure. This one's a little bit more complicated, but we have done it before. Each hydrogen has 1 electron, so that's 2. Carbon gives us 4 more, so that's 6. And then 6 from the oxygen for a total of 12. Carbon in the center, first element that's not hydrogen goes in the center. Bond everything else to that. So hydrogen attached, an oxygen attached. Try and distribute the dots. You can fill the oxygen. Carbon is still short 2 electrons. Take 2 off, put a double bond. You've got methanol. Okay, so here we've got the carbon. It's got hydrogen, hydrogen, oxygen. The oxygen's got a double bond. When we count electron domains, so start with the oxygen, count the electron domains. Remember, the double bond counts as 1. Any kind of bond, single, double, triple, 1 electron domain. Again, why? We're almost there. 2 slides. Okay. Those single domains, 1 domain, so 1, 2, 3, 3 electron domains around the carbon. Start with S. How many P's do I need to add to get to 3? So sp2 hybrid orbitals. sp2. The oxygen, also sp2 hybrid. 1 bonding domain, 2 non-bonding domains, also sp2 hybrid. Hydrogen will only ever have 1 electron domain. That's just no hybrid. We just call that an S orbital. Just uses its S orbital. All right. For a few days now, we have been talking about, counting electron domains, and it's really about double and triple bonds. Okay, so what the heck is going on? Why do double and triple bonds not count for hybridization? Why do they not count for electron domains? It has to do because there are different types of covalent bonds that form. Okay, so the last piece of this puzzle is understanding the difference between what we call sigma. I know. You guys invented a whole slang meme thing that happened to reference a Greek letter that we use a lot in science. So sigma versus pi bonding. Okay, sigma versus pi bonding. Now, this type of bonding depends on where the orbitals overlap, right? Covalent bonding is all about orbitals from different atoms overlapping, adding together, and concentrating the electrons between the 2 atoms. Then the nuclei are attracted to those electrons. So a sigma bond, and this molecule is full of them, happens when there is an overlap directly along the line connecting the 2 nuclei. Okay, so if you have a bond that overlaps directly along the line connecting the 2 nuclei, we call that a sigma bond. This carbon with 4 bonds is sp3 hybridized. Okay, so there is a carbon, and as the 2 carbons get close together, their orbitals interact. As the hydrogens come in, the orbitals, the place where the electrons are, literally changes. The interaction of 2 nuclei changes the shape and energies of the bonds, of the orbitals. That's how the electrons change. That orbital overlap is what forms the bond. If that bond is on the line connecting the 2 nuclei, then that is what we call a sigma bond. A single bond is a sigma bond. Okay, a single bond is a sigma bond. This, what type of bond structure, turns out to be important because it affects how the molecules behave. So C2H6, okay, ethane. The ends of the ethane molecule, because this bond is radially symmetric, are free to spin. And they actually, this molecule is spinning around. Each end is spinning independent of each other. It prefers a fancy word, conformation. That's the shape. When the hydrogens don't line up, so that the hydrogens are offset from each other. That's why they spin. There's random motion that causes one to spin. It affects the other ones, things like that. So sigma bonding, single bonds, always sigma bonds. Line connecting the two nuclei, that's where the center of the electron charge is. Okay? The other type of bonding, and this is where all the double and triple bonding stuff comes in, is a situation where you have a double bond. You can only have one sigma bond because there's only one line connecting the two nuclei. The other bonds have to form parallel to that. Okay? So if you take a p orbital and put it so that it is not part of the hybridization system, it doesn't mix with the other orbitals, you get a bulge of electron density above and below. These two bulges can interact. Okay? I actually have a little model here. Okay, so here is our sigma bond. This is the red ones are two carbon atoms. So I got two carbon atoms. There's a sigma. Do you see that shape? That's the hybrid orbital, in this case, an sp2 hybrid from each carbon overlapping along the line, this line connecting the two nuclei. Then each carbon has an unhybridized p orbital sticking above and below that line. Remember, the p orbital is both of these lobes together. These p orbitals can interact with each other, bringing electrons in between the two atoms. Not quite in the same way as the sigma, the double and the triple. They're not as good at pulling the atoms together because they're off axis. They're above and below, but they still work. These carbons would have two more, right? Hybrid orbitals. So, like, there would be these orbitals sticking out of the carbons, right? One here and one here. And those would be in this model attached to the hydrogens. So, in this flat plane, you'd have the sigma, and then these green guys would be sp2 hybrid orbitals interacting with the hydrogens. Okay. If we go to a triple bond, you end up with sp hybrid orbitals. So you got a green one sticking out this side. You get a green one sticking out this side, and one over here too. And then you have another set of p orbitals. So you have another set of p orbitals, and you get this sort of situation where the sigma is surrounded, and there's a front and a back. Unfortunately, my model set, like, they fall off, so I kind of have to hold them. So you get this, and you got to imagine that it's also here on this side as well. A lot of times we can reference these sigma and pi orbitals, or bonding, I should say, and they'll say, hey, the sigma bond, that's like a hot dog. That's like a hot dog. And the pi bonds are like the bun. It's the bun surrounding the hot dog. And then I like to say, when you get a triple bond, then you got a bagel dog because it's surrounded all the way around by bun. Okay? In terms of what you have to do on a test, it's dead simple. The only thing I've ever seen them ask is count how many. So they would say, hey, look at this molecule. How many sigma bonds are there? How many pi bonds? A single bond is a sigma. Okay? So 1, 2, 3, 4. A multiple bond has a single sigma and then one or maybe two pi bonds. All right? So this sigma and that's pi. And you're just counting. Okay? You're just counting. So we've got 1, 2, 3, 4, 5 sigma bonds and one pi bond. All right? Questions? So when you're counting, you're just counting how many uh, extra lines are there. The first line you draw, that's a sigma. So one of these lines is a sigma. Exactly. If it was a triple bond, you would count that as a sigma and then two pi's. So it is. It's really not that complicated. You just got to count. If it's a single bond, it's a sigma. A double bond is a sigma and a pi. A triple bond is a sigma and two pi's. Okay. All of this requires us to do the Lewis structure first. Okay. So real quick, last example problem. Go ahead, do the Lewis structure for HCN, hydrogen cyanide, uh, and then we can count some things. Hydrogen 1, carbon 4, nitrogen 5, total of 10 electrons. Central atom is our carbon. Throw that down. Single bond hydrogen, single bond nitrogen. We used up 4 electrons, leaving us with 6. Put them on the nitrogen. Nitrogen's full, but carbon is short. Take 2 electrons off the nitrogen. Double bond, still short. Take 2 more, triple bond. You've got your molecule. Okay, so you've got a hydrogen single bonded to a carbon. The carbon and nitrogen have a triple bond, and the nitrogen has a non bonding pair of electrons. Okay, so in terms of counting the sigma and pi bonds, single bond counts as a sigma. What about the triple bond? Think about it for a sec. How do I count the triple bond for sigma pi? Check with your neighbor. Check with your neighbor. So the triple bond is 1 sigma and 2 pi. So altogether, a sigma, so that's 2 sigma and 2 pi. Does the non-bonding pair count as anything? No, this is counting bonds. Non-bonding, no bond. Don't count it. Where does it count? It counts when you're talking about electron geometry. It counts when you're talking about hybridization. Okay? So it will count in situations where, like, if I want to say what's the hybridization of the nitrogen, I got to count it. Okay. So if I'm talking about hybridization on this nitrogen, I'm going to count 1, 2 electron domains, sp hybridization. Same for the carbon, 1, 2 electron domains, sp hybridization. Okay. All right. So we've now got sort of all the pieces we need to go ahead and sort out dyes, which is what our lab is going to be all about. We're going to do a ton of what's known as liquid chromatography. We'll learn all about it tomorrow.